questions. But if you have questions, kind of just jot them down on a piece of paper. Eventually, as we go through and pull all the puzzle pieces together, hopefully you can see the big picture. At that moment in time, I'll tell you, hey, you should see the big picture now. Hopefully everything that we kind of gone over is going to make sense in this case. But if it doesn't at that moment in time, then the questions that you jotted down, by all means, ask the questions. Normally, 9 times out of 10, once you see everything that's going on, you'll be like, I feel okay. I don't have that question anymore. So just picking up where we left off yesterday, one of the things that we said is we're going to have orbitals in this case. And the orbitals are where the electrons need to be found. And we said that when it came to the actual electrons, that they're going to take a path, and the path that they take is going to create the sort of orbitals that we're going to end up seeing in this case. And one of the things that we said is that there's 4 different sort of shapes the electrons can actually make. And they use letters to denote what the shapes are going to look like. So we'll look at the s orbitals, which we did yesterday, the p orbitals, the d, and also the f. We also talked about the fact that there is energy associated with these sort of orbitals, where s is lowest, p is higher, d, and then the f. And once again, as we start to eventually put electrons in, we're going to start saying, hey, the electrons we prefer going in the s, lowest possible potential energy, then the p, then the d, and then eventually to the f as well. All right, here we go. So the s orbitals. So we looked at this one yesterday, and we said that basically when it came to the actual s orbital, the s orbital is going to be spherical. So basically the only thing I'm saying is that if we wanted to find the electron, where the electron is going to be found, is going to be something just on the actual sphere. So if we were to trace its entire location, it would produce a shape that happens to look like a sphere. And one of the things that we said is there's only one type of s orbital, and that's just spherical. That's it. We talked about the actual p orbitals as well. And we said there are 3 different types of p orbitals. There's the px, hey, it's on the x-axis. We got the py, it's on the y-axis, and we also have the pz. So the difference between the orbitals are just their location in space in this case. But they all have the same shape. We said yesterday that, hey, they're like a dumbbell shape in this case, or we can say it's like a figure 8 shape. If you look at the p orbital looks something like this right here. Get it to go on there. There you go. It looks like this. So if you can imagine the electron and you were looking at a p orbital, basically you just got an electron that's kind of like on the surface here, producing, once again, this sort of shape, whether it's the top lobe or the bottom lobe. That is kind of the shape of a p orbital. And once again, when it comes to the px, hey, the px could be maybe this way here. The py, well, okay, this way right here. Or the pz is going to sit this way right here. Now, how many of these do we need? Well, it depends. It depends in this case how many electrons we have. Sometimes we only need 1. And you'll see how we're going to figure out how many we'll need eventually, once we see the big picture. Sometimes we'll need 2, and sometimes we'll need all 3. And if we need all 3, then once again, it's going to look like this in 3-dimensional space, where you have the px, the py, and also the pz. And once again, you have the electron that's just simply making this sort of shape here as it travels on that path. Just like yesterday, one of the things that I told you is that I can hold you responsible for, once again, drawing these on a test. And I told you yesterday, if you have something like a px, you're just going to label one of the axis x, and you'll put that shape on the x-axis. I'm not going to ask you to draw in 3-dimensional space. If I said, hey, I want a py, then go in here and label one of the axis y, and then once again, show the shape. Don't forget, this picture doesn't really do justice here. In this picture, it looks like the 2 lobes are actually touching. There is actually an empty space that exists between there. And if you remember, we said that empty space is referred to as a node. It's just a place where the electrons not be found. I also told you that I'm not holding you responsible for that term either. Just realize there is a space. Why does that space exist? Well, again, once you see the full picture, you'll be like, oh, that does make sense that we need that space to be there. Then I ask you to draw, once again, the pz, and keep in mind on the test, I'm going to only ask you to draw one of these. Choose whatever axis you want. Just, hey, you want to call this the z-axis? That's perfectly fine. In your 3-dimensional space, I will accept it. I just need to see that that lobe is on the actual z-axis in this case. So those, once again, are 3 different types of p orbitals. And then it came to our d orbitals. When it came to the d's, there are 5 different types of d orbitals. We've got the dxy, the dyz, the dxz, the dz squared, and the dx squared minus y squared. If you look at 4 of the 5, they look the same as far as their shape. They kind of like 4-leaf clovers here. And when you look at the actual designation of like the dxy, and if I ask you to draw the dxy on the test, you should say, if anything, thank you, because this is going to be really easy for me to do. All you're going to do for the dxy is you're going to write here, dxy. You're going to draw your x and y axis, and you're going to put your 4-leaf clover in between the x and y. It's as simple as that. If I say, hey, I want you to draw in this case the d, what's the next one I got up there, yz. Then you're going to say, oh, no problem, Mr. Harrelson. I'm going to label this one y, maybe this one z, and I'm going to draw my 4-leaf clover in between that axis. If I said the d, xz, then you're going to say, okay, I'll label one axis my x, the other one z, and the 4-leaf clover is sitting in between the x and the z axis. So for these 3 right here, just place them between the axes. You're done with them. The dx squared minus y squared, that one's pretty easy. Dx squared minus y squared. You're going to label one axis your x, the other one your y, and you'll show your 4-leaf clover on the actual x and y axis. So those are easy. The only one that is different is that dz squared. The dz squared looks like a p orbital. Hey, I'll label this z here. Here goes kind of like my p orbital. What makes it different is it has like this donut that's going around it, which means the electron can exist on that lobe there, it can exist on that lobe right there, or it can exist, in this case, on that donut ring that's going there. So it has these different paths that it can actually take. So if you look at the actual d orbitals, the d orbitals look like this. 4-leaf clover. Once again, electron can take a path to produce this lobe, or that lobe, or this lobe, or that lobe right here. And once again, the difference between these are just, hey, maybe this is going to be my dx squared minus y squared, because it's exactly on the x and y. Another one's going to be like an angle like this, or an angle like this. But in 3-dimensional space, it gets a little complicated seeing exactly all these different shapes that the electron is making. But there's 5. That's the key. Make sure you remember there's 5. So I got, and watch this. There's 1 of the s. There's 3 of the p's. There's 5 of the d's, which means that when we go to the f's, there are going to end up being 7 different f orbitals here. And when we look at the actual f orbitals, they become even more complicated. For instance, I've got in this case the 4f cubed minus 3yx squared, 4f 5y z squared minus yr squared, 4f 5x z squared minus 3xr squared. I've got the 4f x cubed minus 3xy squared. I got the 4f z x squared minus zy squared. I got 4f xyz, and I got the 4f 5z cubed minus the 3zr squared. Whoa, that's a lot. What I need you to know in this case is I need you to know this right here. There's 7 different f orbitals. I am never going to ask you to draw the f orbitals, nor am I going to ask you what their designations of these f orbitals happen to be. They're just very complicated orbitals that are out there. Now, sometimes you'll notice in my notes, you'll see like, hey, I've got in parentheses A, or I got parentheses G, or I got parentheses D. Does anybody know what those actually represent? A lot of times in the notes, when you see it, what Claire was going to say.
Isn't it all like the class ended?
Exactly. So it's like my, letting me know where the actual class ended. And sometimes I just don't get around that, like cleaning it from, or scrubbing it from the notes for the previous year. Look at that right there. I leave this one intentionally. That's nostalgia right there. That's when we used to have 8 periods at visitation. 1, 2, 3, 4, 5, 6, 7, 8 periods is how many we had. Each period was like 45 minutes. I thought it was a pretty good thing. Keep in mind, did students have to have 8 classes? Absolutely not. So what ended up happening is you had periods in the day that you had free periods in that case. So instead of all having like the cub period free, you would just have different free periods. So even as a freshman, you had free periods that were sitting there. But that's when we had 8 periods in a day. All right, continuing on here. So what we're going to look at is when it comes to these actual energy levels. The energy levels themselves are going to also have what are referred to as sublevels. And when we look at sublevels just indicate the type of orbitals that are available to a given energy level. You're going to see how this plays out in 1 second. So for instance, one of the things that we're going to see is that there's kind of like a draft going on here. When it comes to the first energy level, it's like, hey, I want to draft an orbital, but I want to go with the lowest possible energy. So it's like, I'm going to draft an S. The second energy level is like, I get 2 drafts. So who do I want to draft? I want to draft the lowest orbital as far as its energy, S. I'm going to draft a p orbital as well. The third energy level is like, I get to draft 3. So it's like, okay, I'm going to take the lowest S, the p, and then I'm going to go with the d. The fourth energy level is like, hey, I get to draft 4, S, P, D, F. And then once you go to the fifth energy level, it's going to be S, P, D, F. And that's all it has. We're just going to stop S, P, D, F, because we said there's really only 4. Technically speaking, don't write this down. There is a theoretical G orbital as well. Remember, all these orbitals were not discovered experimentally. Remember, Schrodinger used mathematics and calculus, and he figured out what the shapes were. Then he went and did the actual experiments to confirm that, hey, oh yes, the electron is kind of doing the spherical thing. Or maybe it's doing this actual dumbbell shape. Or maybe the 4-leaf clover. Or maybe those complicated Fs. So theoretically, there is Gs out there. Only problem is there's not enough electrons to fill up the actual G sublevel. All right. The next thing that we got here is each one of the sublevels. Remember, that's just an S orbital, that's a P, that's a D, and an F. But each one of the sublevels has a certain number of orbitals associated with them. And when you look at this grid, initially it's like, oh, that looks a little complicated there. But in actuality, look what's going on here. How many type of S's do we have? 1. There's just one type of S. Okay, that's how many orbitals you got. Right here, for the second energy level, it's like, hey, I got 1 S because we got an S orbital there. And remember we said there's 3 different types of P orbitals? Well, that's all I'm simply saying. So if I look at the second energy level, in total, it's got 4 different orbitals available to it. When I look at the third energy level, it has the S, well, there's 1 type of S. There's 3 different types of P, and there's 5 different types of Ds. So in this case, it's got like 8 different orbitals available to it. And then the same thing. Fourth energy level, it's got 1 of the S, 3 of the Ps, 5 of the Ds, and then 7 of these F orbitals sitting here as well. All right. Next slide simply says that each orbital can actually hold a maximum of 2 electrons. Which means, if they can each hold a maximum of 2, hey, that means if I only have 1 set of S orbital, it can hold max of 2. Hey, this S orbital, which we only have 1 of them, that 1 can hold 2. The P's, we said there's 3 different types of P orbitals. If each P can hold 2 electrons, then that means, hey, in total, the P orbitals can hold a maximum of 6. Just like the D's, there's 5 different D orbitals. Each one can hold 2. It maxes out at 10. The F's, there's 7 different F orbitals. Each one can hold a maximum of 2. They will max out at 14. So even when we look at the maximum number of electrons, S can hold 2, P can hold up to 6, D, if I have all the orbitals, can hold up to 10, and F can hold up to 14. Once again, at this point, I don't expect you to see how all these things are going to pull together. You will if you do. I just got to give this information, and then we're going to get there in 1 second. This last slide here, and then we're going to see if we can tie a little bit of this stuff together. It simply says that when we look at these sublevels, remember the sublevel right here, this first energy level has a sublevel of S. Well, the second energy level is like, I have an S too. The third is like, I have an S. The fourth says, I have an S as well. One of the things that's going to happen is when we look at this energy level and this sublevel versus this energy level and this sublevel and this one and so forth, the actual orbitals are going to get physically larger. Meaning that when I look at it, here's my 1s, which is spherical. For the second energy level, it's going to get larger. And the third energy level is going to get larger. And if I have the fourth energy level and it's s, it's going to even be larger. Once again, this is going to make sense once you see it. You're going to be like, oh, it's logical. It's got to be larger in this case. So right now, we're just going to accept it at face value, and then we're going to come back. And I'm going to, once again, show you why this has to be the case. All right. What we've got to do in order to really tie all this stuff together is we got to go over 3 different rules here. And these 3 different rules are going to govern how we're going to take electrons and place them in the atoms. And we're going to look at the Pauli exclusion principle, Hund's rule, and Aufbau principle as well. And eventually we'll get to electron configuration, and I'll probably get there maybe tomorrow. So here we go, orbital diagrams. One of the things that we're not going to do is we're not about to sit here and draw these orbitals when we're trying to show where all the electrons will be located. It's just way too complicated to take these orbitals that, once again, exist in 3-dimensional space, some on the axis, in between the axis. It's just too difficult. We're not going to do it. So instead, what we're going to do is create what's called an orbital diagram, where we're going to use dashes, and I'll show you how this is going to work, to represent the actual orbitals. So we're using dashes to represent them. And once again, before we start putting electrons into this orbital diagram, I'm going to show you how to create it. We got to go over 3 rules that, once again, govern how to place the electrons in the orbital. First rule, I don't know. This guy is in every single chemistry textbook. And it's this rule called the Aufbau Principle. I don't know if it should really be in there. And the reason why I feel like I don't know if it should be in there is I just think he kind of stated what was the obvious. He simply said that, hey, electrons will enter the lowest possible energy level first. So if given the choice, it would go to the first energy level because it's lower in energy versus the second. If you remember, we even said that when it came to these sublevels, S was lowest in energy, then it was P, then it was D, and then F is the highest in energy level. If given the choice, it's going to S before it actually goes to P. Why do I say I don't give this person a lot of credit? Is an electron is a form of matter. It's almost like me saying, hey, Mr. Hurlson's going to have the Hurlson's principle. And the Hurlson principle states that, hey, the actual expo marker will go to the lowest possible potential energy. It's matter. Every form of matter always seeks that lowest possible potential energy. He took an electron, which is just a really small piece of matter, and said the exact same thing. That's why I don't know. I don't know if he really deserves all the credit he gets, because I think it's just obvious that everything seeks that lowest possible potential energy. The next one we have is you have the Pauli exclusion principle. And the Pauli exclusion principle simply states that you can have a maximum of 2 electrons per orbital. And when we have these electrons placed in the orbitals, they gotta have opposite spins. What does it mean by opposite spins? I'll show you that in 1 second. The last rule, which is called the Aufbau Principle. Not Aufbau, but Hund's rule. This particular rule I can't address yet. Once we get there, I'll kind of show you how that rule is going to come into play. So here we go. Let's get started here. What I'm going to do here is I'm going to build an orbital diagram. And you're going to write this down, because one of the things you'll be doing is you'll be creating some of these orbital diagrams as well. So I'm going to start over here. And what I'm going to do is I'm going to write down the following. I'm going to say energy level. And we're going to look at hydrogen here. So hydrogen, and what I know about hydrogen is hydrogen has 1 electron. I'm going to write the hydrogen over here. Kind of move it over just a little bit. Hydrogen, once again, 1 electron. All right, under energy level, I'm going to put a N equals 1 here. Why did I put N equals 1? Because I know, given the choice, the electrons want to seek out lowest possible energy. Aufbau principle. It's not going to the second energy. That's higher energy. It's not going to the third. So it's going to go to the N equals 1. So what I did here is I'm going to put a dash to represent its energy level. So that's kind of like its, let's put a little labeling here. That's my energy level. The next thing I'm going to do is I'm going to do just a couple of dashes. How many dashes you do, it makes no difference. You can do 2 dashes, 3 dashes, not really that important. I just need a dash to separate these two things. I'm going to put one longer dash right here. And this is going to represent, in this case, my sub-level. Now, the first energy level, if you remember, we said the first energy level, it got to draft only one type of sublevel. And that type of sublevel happened to be, what's the SPD or F? Which one was it? S, because once again, it's drafting the lowest possible energy sublevel. So what do I do here? Just for clarity's sake, so you can see where this number comes from, I'm going to make this, that one's dead, let's throw it away. Don't want it sitting up here, because I'll just try to use it again. I'm going to put the 1 right here in red. Right here, I'm going to put 1. I'm going to put an S there. I need to make sure that I keep track of these S's, because once again, eventually we're going to see that second energy level has an S. Third energy level has an S. I just simply say that S belongs to the first energy level. Now we said hydrogen gets 1 electron. The way that we designate the 1 electron is we're going to go with what is called a spin up. And that's what that arrow means. It simply means spin up. I'll explain what a spin up means. So this is spin up, and eventually we'll see a half an arrow going down, and that's called a spin down. I'll explain. So, what does this orbital diagram actually represent? And once again, this, I'll go right up top here so we'll know. This is my orbital diagram. What it represents. And keep in mind, this right here, just so we're clear, that's kind of like my sub level here. What does it represent? It just tells me what's going on with the hydrogen's electron. It says if you want to go find hydrogen electron and figure out what it's doing, you go to the first energy level. What is that electron actually doing? Well, it's doing the following. Here goes my sphere, and the electron is just on the surface of that sphere. So that's it. It's just traveling and it's producing a sphere. What does a spin up versus a spin down actually represent? The electron itself is actually spinning. One of the things that we used to do when they make it far enough in conceptual physics, and they talk about this thing on the electrical field, which I know last year we didn't make it there, they might make it there this year, is a lot of times when things spin, they produce electrical field. That's not important. But in conceptual physics, one of the things that we do is we do kind of like the right-hand rule. Where if you say that, hey, something's spinning this way right here, look at my thumb. It's spinning up. And technically, when you learn about electrical fields, the electrical field is pointing up. That's irrelevant. But my hand, my thumb is pointing up here. If I take the same hand and I go in the opposite direction, I must take my hand and I gotta turn it this way here. And now my thumb is pointing down. The only thing I want you to point out is that when the electron is on the actual surface, so it's on the surface here, it's literally spinning in one direction. And as it's spinning, it's taking a path to produce this shape right here. So one of the things we're going to see is, remember, it said in the Pauli exclusion principle, no more than 2 electrons per orbital. And then, once again, if we have 2 electrons in an orbital, they got to have opposite spins. And I'll show you how that looks in a second. So literally, this is the orbital diagram for hydrogen. That's it. Orbital diagram for helium. Watch how this one's going to play out. For helium, helium has a grand total of 2 electrons. So when I create its orbital diagram, the first thing I'm going to do is I'm going to go here, I'm going to write down the energy level. So here it goes, N equals 1. As helium is like, I want my electrons, once again, to sit at lowest possible energy. I'm going to draw a line to represent the energy level, and then dash, 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 and then draw my sublevel right here. And once again, for clarity's sake, so we know where this 1 comes from, I'll use the red here, 1, and I'll have 1 S sitting right here. So if I look at helium, helium has 2 electrons. First electron will be spin up. Second electron is going to be spin down in this case. Because that's what, once again, Pauli exclusion principle. No more than 2 electrons. and they must have opposite spins. Which means that when we look at helium, what does this really mean for helium? It simply means that when we look at it, we've got two electrons that are making the path of this orbital. One electron is spinning as it's on the path, it's spinning in one direction, clockwise. The other one is spinning counterclockwise, and that's why we got the spin up and the spin down. But there's now two electrons that are producing the path that produce this particular shape. That's how, in this case, helium looks. And helium is different from hydrogen. Hydrogen only has one electron. Helium's got two electrons producing this polar path going on here. If we go to the next element on the periodic table, which will be the third element. The third element on the periodic table is going to be lithium. Where's my eraser? Here it goes. This is where it gets fun. Lithium, Li. 3 electrons. So that's what it's got here. So what do I do here? I'm going to go in and I'm going to do the following. Let's say energy level N equals 1. Here goes my energy level, dot, 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 dot. Here goes my sublevel. And once again, I know that it gets to recruit the 1. Let's take the lowest one, 1s. All right, here we go. Spin up, spin down. That takes care of 2 of my electrons. I got a third one here. There is a problem with the first energy level. The problem with the first energy level, it's like going to some place like Rehoboth Beach, Dewey Beach, Ocean City on maybe Memorial Day weekend, or maybe going there on the 4th of July. As you go to the various hotels, you're going to probably see something in the window that says what? On the 4th of July, you just sort of show up at Ocean City or Dewey Beach or Rehoboth. What's going to be in the window most likely?
No rooms left.
No vacancies, no rooms left. That's exactly what the first energy level says. Like, I don't have any room here. You can't go in here. Which means what's going to have to happen is we're going to have to go to the second energy level. So N equals 2. Now, if you remember, we said for the second energy level, the second energy level has 2 sublevels available to it. It has the S that it will recruit, and it will also recruit the next lowest, which happens to be who? The P. And if you remember, one of the things that we said already, we said, hey, S is lower, P is higher, D is higher, F happens to be higher. Watch how this is going to work out. Let's see what's going on here. Initially, you look at it, you're like, whoa, wait a second. This shows, because if we look at it, energy is increasing as we go up this way here. So increasing energy. Because remember, we said, hey, first energy level lowest, second time. So we're showing increasing energy here. This shows that, hey, the 2s is lower in energy and the 2p is higher in energy. Question I have for you. Why, oh, why did I do 3 dashes for the 2p's? I do 3 dashes there. Nobody sees it. Claire.
Is it because there's 3 P's?
Man, you're on it today. Absolutely. Because there's 3 different types of p orbitals that we have. So we got 3 dashes. Eventually we get to the D's, we're going to have 5 dashes. We get the F's, we're going to have 7 dashes here. Now when we look at this, basically what's going to end up happening is because helium or lithium has 1 more electron, it's going to go right here. Technically, the 2p orbitals don't exist. Because in order for the orbitals to exist, the electron has to be making the path, taking that path to produce it. Now, watch how this is going to play out. Let's say that, hey, man, that was awful. I can't believe I missed it. On this actual yellow sphere, it's not the best handwriting, it's just really small for me to write on here. What does it say? It says 1s. So what we can imagine here is I've got 2 electrons. They're on the surface and making this 1s in this case. But then what's going to end up happening, I need the 1s to go inside the 2s. The 2s is going to have one electron that's on the surface right here as well. Wait a second. We said the 1s is smaller, the 2s is larger, and eventually we get to the 3s. It's going to engulf this whole thing. The 4s will engulf everything as well. So the orbitals are going to get larger as we go to associating these orbitals with the higher energy levels in this case. So once again, lithium has 2 electrons on that inner sphere and just 1 electron that happens to be on this sphere right here. And keep in mind that when you start drawing these orbital diagrams, you don't have to write this down. I tell students to do it just to get in the habit of knowing how this thing is going to split, but it technically doesn't exist. There are no electrons that happen to be in the 2p. What we're going to do here is we're going to move all the way to, what can we go to here? Let's go with this one here. We are going to go with, it's a good one. Let's go with carbon. Oh, here we go, carbon. Carbon has a grand total of 8 electrons. Wait, make sure that's right. 1, 2, 3, 4, 5, 6. It has 6 electrons, Mom. It's got 6 electrons. So, yes, absolutely. So here we go. We're just going to start all the way from the beginning again. So I'm going to go N equals 1. Here we go. And then we go dash, 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 dash. Here we go. And we just get an S here. So we get a 1s that sits here. I'm going to go, hey, first 2 electrons, 1, 2. I'm done here. Then I'm going to N equals 2. Because once again, that energy level is completely filled. I need to go to the second energy level and bring that one in. N equals 2. I'm going to take this one. 1, 2, 3. I'm going to go here and simply say, okay, I've got this. This will be 2s, 2p. I've got a grand total of 6 electrons, so here we go. 1, 2, 3, 4, 5, and now I need to add my 6 electrons. So here goes the interesting point. Do the electrons want to exist, and don't write this down, do these negative electrons prefer existing like this, or do they prefer existing like this, these negative electrons? Which one would they probably prefer, Benny?
The first one.
The first one. Why would be the first one?
Because, like, the more stable elements tend to have, like, fuller spheres, if that makes sense.
Yeah, you do. You're with me. I understand exactly where you're going, because you're actually jumping ahead a little bit further in advance of where I would have been. And you're right. But you gotta have, I can't go into it, because I'm gonna say it, it's not gonna make any sense when I try to go into it. Go ahead, Benny, try it.
Okay, so is it because, like, their, like, energies are, like, counteracting each other to, like, balance out? That makes sense? Like, spinning and opposites?
Technically, this is not the right one. I know where you're going, and I can't explain it because we haven't gotten there yet, because there is going to be this thing known as stability and having completely filled sublevels. We're not quite at being completely filled. Technically, electrons are going to go like this right here. And the reason why is electrons are like, hey, I'm negative, you're negative. 2 negatives come together, that sounds like repulsion to me. I don't want to have to deal with this sort of repulsion. So what it's doing is it's simply allowing the electrons to exist in separate rooms. Even if you think about it, this is analogous to you moving into a new house. Hey, we move into a new 5-bedroom house, and it's me and my other sister. And there's clearly all these other rooms here. Are we gonna pair up and be together when we kind of like are very similar in nature and kind of repel each other? I'm like, no, you go to your room, take your room. I'll take my room. And that's the exact same thing the electrons are doing here. And this is where Hund's rule comes into play. Hund's rule simply states, and that's the one I told you I had to kind of skip over really quickly. Come on back. There we go. Don't turn it off. Hund's rule. When electrons occupy orbitals of equal energy, these are orbitals of equal energy. One electron enters each orbital until they are forced to pair up. So I would go one electron here, one here. Now once I have 3 electrons, I got no choice but to force them to actually pair up in this case. How much time we got left? Got 4 minutes here. What I want to do is I want to go all the way to, let's go to nitrogen. No. I'm going to do nitrogen. We're going to sulfur. So we're going to go all the way to sulfur. And sulfur, based upon my periodic table, it has a grand total of 16 electrons. Wow, that's a lot of electrons there. And what I do is we're going to see if we can actually build the orbital diagram for sulfur. So let's see how this is going to play out. So here we go. So I'm going to start off with my first energy level. So sulfur, 16 electrons. So to start off with the first energy level, so N equals 1. Energy level, sublevel. First energy level, it gets to recruit the S. Okay, here we go. Well, that belongs to the first energy level. 2 electrons. 1, 2. Got it. Well, completely filled, so it's time to go to the second energy level. N equals 2. Second energy level. 1, 2, 3. So I got my 2S and my 2P. So we had 16 electrons in total, so let's see what we got going on here. I took care of 2. So 1, 2, spin up 3, spin down 4. 5, 6, 7. Gotta go once again, each individual orbital here. And now I'm forced to pair up. So I've got 7, that's 8, 9, 10. I got 16 here. Yes, absolutely. So watch this last one, because this is the one I need to show you in order for you to be able to do your homework assignment for tonight. For this one, we're going to go to N equals the third energy level. So N equals 3 here. I just want to show you how we'll draw this third energy level. Third energy level has 3 sublevels. It recruits the S, the P, and also recruits the D. And the way that you'll draw this one is going to look like this here. Remember, there's only one type of S. There's 3 different types of P's. Remember, we said we had 5 different D's. 1, 2, 3, 4, 5. So that's it. So now when I go in, I'm going to go in here and kind of draw this thing. I'm going to go, hey, 16 electrons. We already took care of 10, 11, 12, 13, 14, 15, and 16. This is the orbital diagram. Now, what's going to happen on your homework tonight is your homework is going to consist of you creating some of these orbital diagrams. The biggest your orbital diagram will be this right here. The only thing I'm going to ask that you do not simply take this orbital diagram right here and kind of have it as a shell, like you erase all the electrons, copy and paste it, and then put the electrons in. You've got to get used to drawing this. If you don't practice drawing it, you're going to forget how to split it, and when it comes out this test on Thursday, for the next test, you're going to miss some free, easy points sitting there. So on Veracross, it's going to tell you to go into the worksheet packet. It's going to tell you exactly what to do. And you're just going to recreate these orbital diagrams for a couple of the elements out there. And then tomorrow we'll come into class and I'll give everybody the opportunity to take one of these orbital diagrams and place it on the board. So everybody's going to do one of the orbital diagrams and place it up here. So make sure you have it completed for tomorrow. I will see you mañana. Enjoy the rest of your day.